Hello, welcome back to another lecture in this simple operating system from scratch low-level programming tutorial. I'm going to carry on from last time, and we're going to do something very useful in this lecture, and then we're going to have a bit of a detour just to play around with the ideas that we've got, just to learn a bit more about the computer and confirm stuff that we've assumed. So in the last lecture we talked about how to define functions in assembly, and if you recall, there's not really a function. The computer doesn't really see functions, it just sees jumping around the code, and as far as the CPU is concerned, a function is just a jump to somewhere, and then it just jumps back to wherever it jumped from after it's finished that code. And if you remember, it used the stack when we used the call function on an address. Then all the CPU does is it pushes the next address onto the stack that will execute when we return from that function, executes the code, and then when we call the return operation, CPU function, it just pops off that return address and jumps back to it, and that's all it does. But with this we can build kind of an abstraction of functions. And we created a function for printing a string, an null terminated string, so we could print hello world. And when it got to the 0 in the end, it stopped printing the string. So it basically, the function just looped for each character until it got to the ASCII character 0, or the 0 byte, the null byte, and then it stopped. So that was useful. But what we're going to do now is look at how we can print a hexadecimal value to the screen. So it's okay printing characters, so we could print strings that we find in memory, and we'll look at that later on, or we can print our own strings. But if we want to see what's inside memory, if we want to look at the values that are stored in particular addresses, which is what we're going to do, then we need some way of printing a hexadecimal string on the screen, and so we're going to look at that. So the CPU doesn't help us there. It doesn't, like I said, it doesn't really care what's stored in memory, whether it's data or strings. And it doesn't really see strings. It's just that when we choose to print a section of memory, if it does happen to have values for the bytes that map to readable, printable ASCII characters, then it will print them out. And if we just print a random piece of memory using our printstring function, it will just print some random characters, or none at all if there's no characters for those particular values, until it reaches 0. Anyway, so we're going to look at how to print a hex string to the screen. Once we can do that, it then gives us a way to inspect memory and see what's in there, and that's quite interesting, but also it's going to be useful when we come to load our kernel. So currently all we've got is our boot sector that was loaded, 512 bytes, which BIOS loaded, and later we're going to want to pull in some more sectors off the disk that have our kernel code in, and then transfer execution to the kernel code. So we need to be able to read memory and display it on the screen, so that while we're developing this, we can verify that we did in fact read some sort of pattern, some sort of data that we know, some known data from the disk into memory. We can confirm it's there by printing it with our hexadecimal printing function. Okay, so let's do that. Okay. Well, what we've got so far, I've just started out with the code that we had from the last lecture really. Let me just explain this. So first of all, I set up my stack. So this is my boot sector. I just set up the stack to make sure it's clear of my code, so that if I push things onto the stack, I know that it's not going to overwrite my boot sector code. Because initially when BIOS loaded me, I didn't know where the stack was, so I've set it explicitly so I know where it is. So I set it there, 8000 hexadecimal. And here I'm going to define my printx function. At the moment it just does nothing. So the way this is going to work is that I'm going to move a value into the dx register. So this is my argument for this printx function. Remember, I said that there aren't really arguments. We just have, as long as the function knows where to look for something that we want to pass into it, then we just pass it into that thing, and we have this agreement between when we call the function and inside the function where it gets its arguments from. So I'm just using the dx register. So I pass this function in, I pass this value in, and then I call printx, and what this should do is print that hexadecimal on the screen. So what that translates to is that we're going to have to print for this. So remember when we write hexadecimal, when we relate that to binary, this number with 4 hexadecimal digits represents 2 bytes, 16 bits. Okay, so so these 2 digits represent the high byte, and these 2 digits represent the low byte. And if we want to print a byte to the screen in hexadecimal, then we've got to print the 2 separate digits, the 2 4 bits. So we've got to translate those into ASCII characters. In this case, the ASCII character the ASCII character that is the number 1, and then the ASCII character numbers 2, and then the ASCII character number 3 and 4. So we have to translate it into ASCII to print that. Okay, so then we call printx. I said before that it's useful to reuse stuff that we've done before, so we wrote a function before that printed a string to the screen. So let's reuse that in our printx function, and here's a way we can do that. I'll start off with that. I'm just including my functions in here, just so I can keep that in a separate file, but this is just a print string function that we worked on last time. Okay, and it takes as its argument the SI register. Well, let's just fill this out so that if I run it, so it's a good idea to run your code to see what happens. Okay, it does nothing, so it boots up and it goes into an endless loop and it doesn't print anything. So let's start to build this up. And like all things, it's good to start off small and just build it up. I'm not going to be optimizing things here, it's too early to do that. And so you can optimize things later on if you can make them work in a roundabout way that at least you understand how it's working and you're learning how to use the assembly instructions and the registers, then you can optimize it later. So what I'm going to do today is not optimized functions. I'll leave that to later. So let's get on. So we're going to have this printx function. So I said that we should reuse our print string function. So one way we can do this, a nice way, is that if I define a template for printing a hexadecimal number, like this, if I do now I'm going to call it, let's call it hex template. Okay, so I'll just define this as a label, and then I use this is how I declare data in my assembly code. So in here I'm just going to put OX, because that's often, so we know it's hexadecimal, we often have 0x at the start of the number, otherwise it's confusing whether it's decimal or hexadecimal. So there we go. I'm going to do it like this. I'll put a space on the end so that if we print out multiple numbers, they're separated, just to make it a bit neater on the screen. But this is where I'm going to start. So if I now call my print string function, and the argument for print string is the SI register, so I'm going to move SI hex template. Let's just check this does what I expect it to do. And as always, I say that it's very likely that I'll make mistakes when I'm doing this, and you will too. Assembly is difficult to remember how to use if you don't do it on a day-to-day basis, and it's easy to make mistakes, but it's more learning about how it works that helps you to get past those things. So if I make mistakes, then it's just a bit of fun, and I don't mind. So what did I do then? So I've defined this template string that when I call my printx function, I move the template string, the address of it, into the SI register, and then I call print string, so it's going to print each of these characters. Okay, and that's what it did when I loaded it. So that's the printing part done, and like I said, it's good to reuse stuff. The way that software is so powerful and computers are so useful now is that it's just layers and layers of software, and you don't want to have to keep rewriting things. And also you might introduce bugs if you do similar things but slightly differently. Okay, so we're doing it like this. It's a nice way. So the goal now then is, what I'm going to do is, really I want this to print OX1234 there to represent this value. So I'm translating this value into a string. So to do that, this is my strategy. I'm going to replace these question marks with each of these digits. So let's, like always, let's try and build it up. So we'll just see if we can get the first one, the first digit in there. So this is in memory. When my boot sector loads this hex template, this string is going to be stored in memory somewhere at some offset, which we can use X template label to reference. And what that means is that if I want to change this byte of memory, then I can reference hex template plus, well, that will be plus note, that will be plus 1, and this will be plus 2. So if I want to change this byte in memory to an ASCII value for the digit in here, then I can reference it as hex template plus 1. So let's just have a look at that. First of all, we'll just stick something random in there to check that we can change it. So let's, if I do move, now what's the easiest way of doing this? Let's have a look. Let's just play around with some things here. So if I try this, so if I move into hex template, let me just stick an A in there. Let's see what this does, or if it works even. Okay, so there's a problem there. First of all, it doesn't know how big of a value I want to move in there. So if I just put here byte, let's try this. There we go. So I've moved that byte A, the ASCII character A, into that template. Now you can see here that it's at the start, and I didn't want it there, I wanted to move it there. So I'll do X template plus 2, and that should put it in the right place. There it is, so now it's OXA. Okay, so I can see that I can replace those question marks in my template, and all this is doing when I compile this hex template plus 2, my NASM compiler will just compute this when it compiles it, so it'll know that this is the offset for hex template in memory, and it will just add 2 to it. Anyway, that's how I can change that byte. So now the question is, how do I get that to equal 1? Which is the first 4 bits. It represents the first 4 bits of the high byte of this 16-bit value I want to print. So let's have a look. So let's try moving. Well, first of all, we've got this dx here, okay, and we want to isolate that first 4 bits. Now one way we can do this is to mask it and then shift it. So to mask it, we can use this AND command. So let's just say that we move, let's move dx into bx. Just because I don't want to be changing the values stored in the thing I'm printing. If I start modifying the argument that I'm printing it, I'm going to mess things up. So I want to preserve it. So I'm going to do this move dx into bx. So now bx will contain this OX1234 value. Okay, let's just check this works. Okay, so it's printed my A. So now if I do, okay, I've got that in there, and what I want to do is isolate that first 4 bits, that 1 of the high byte. So what I can do first of all is I can AND it. In fact, in this case, I can just do this. I can shift it right. A good way to see how this works is just to run our code, and then you'll get about. I can explain what the instructions do, but we can see them working, and that's a good way of doing it. So what I'm going to do here is I'm going to say shift right the contents of bx by, and then a number of bits to shift it right. Now, what I want to do is move this 1 here all the way down to the least to the lower byte, to the lower 4 bits of it, because I want to print it. Let me just, if I just show this. So I'm going to shift right by how many bits do I want to move it by. So, well, how many bits are in the way for it to get down there? Each of these is 4 bits, so that's going to be 3 times 4. So I need to shift it 12 bits down. Okay. So shift it right by 12 bits. So now in bx, what we should have is just the number 1. It's representing this first digit. So let's just see that. So if I now try this. So what I'm doing now is bx had this number in it, and I've shifted it by 12 bits to the right. So now this 1 is in, so now it looks like this. In fact, if I write them in comments, which is always good. So if I do, this is what's happening here. So bx is now going to ox 1, 2, 3, 4. And now when I've shifted by 12 bytes, we're going to get this. Bx goes to ox. Okay. Which means that it now just holds the value of that very first digit, 1. Which is good because we've isolated those 4 bits, which we want to turn into an ASCII character to print that. So now what I'm doing is I'm saying move BL, so the lower byte of the BX register, so this bit, into position in the hex template to the first question mark here. Let's see what happens then. Let's see if this does what we want. Okay, so what we've got, well, we've got something in there which is good, but it's giving me a little smiley face now, which just means that it's not trying to insult me. It's just that the value I put in there doesn't represent the character that I want to print. The value that I put in there is a 1, and 1 doesn't translate to an ASCII character, to the character 1 in the ASCII table. Let's load the ASCII table up and see. Okay, so the ASCII character for the number 1, which is what I want, is actually hexadecimal 31 or decimal 49. So the number 49, the byte 49, maps to an ASCII character for the digit 1. The one that I've copied in there is this one. I've copied the value 1, which maps to some non-printable character. Okay, and that's why I've not got a printable character. I've just got some random character. So I want to convert that now to the ASCII value. Now an easy way to do this is, well, first of all, let's do it manually. So we know that the value I've printed is I've got a 1 in there, a byte 1, but actually I want to raise that up until it's the value of the ASCII character 1, which is 49. So I think if I add 48 to that number, to the number in bx, so if I do add bx 48, and because I've not put this on, I mean decimal 48, let's see what happens now. There we go, we've got a 1. So we've now converted that 4-bit value into an ASCII character 1, which is what we want. So we're getting very close now. It's always good to build things up like this. But what we want to make this a bit easier, so a little trick to do this. And again, there are more efficient ways of doing this, but we don't care right now. I'm going to define something called a hexabet, which just translates to an alphabet for hexadecimal characters, and this will make it a bit easier for me to, well, very easy to convert between a value like a byte 1 and the ASCII value 1, or the byte that represents, say, E or F in hexadecimal to a character E or F. So an easy way to do that is if I define my hexabet down here. So I'm going to just have note 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So they represent all of my possible hexadecimal digits. So now all I have to do is, if I want to map the value that I've stored in this bx value to a character to print to the screen for that digit, then I've just got to use this, just index that value within this label, hexabet. Let me just do that, let me become clearer. So what I want to do now is translate what's in bx into an ASCII character. Now we can do this, and I think if I do move bx, and let me think, I should be able to do move bx and then bx, so whatever is in bx, which is the value that we want to translate to, so this is like the number that we want to translate to the ASCII character, and if I do hexabet, see if this will work. Sorry, that's the wrong one, so hexabet. See what this does. I've got a 1 there now, which is good. Now let me just check that this is working by, what if I put an E in here, for example? It's just going to print, it's just going to map it to the right character. Ah, yes, it's got an E, so you can see there, so we're on the right track now. Now let me just explain what I did there. So what I'm doing is the value stored in bx, after I've shifted it, is the first 4 digits, represents the first 4 digits of this. Let me put it back to 1, just so that we're consistent. And I want to convert that into the ASCII character for that digit. So if I want to convert the digit 1 into, so the hexadecimal digit 1 into the ASCII value 1, I've got to change it to the character, ASCII character for 1, which is this. So what I do is because I've defined all my ASCII digits here, I just do a lookup. And what this does here is it says, take the address of the hexabet, which the address will point to character 0 initially, and then add the value to of bx, so the digit that I want to print, to hexabet, and store that back into bx. So it's converting bx into the character to represent the value that wants in bx. And so if it was 0, it would map to that first character. It would be hexabet plus 0. If it's 1, it would be hexabet plus 1, so it would go to there. So this is doing my conversion, and this is exactly what I wanted. That's good. So just to explain, there's a difference between these two things here that look the same. I mentioned earlier that when you're writing stuff in assembly, sometimes you can be misled a bit as to what's actually working under the hood. Now what this is doing is the assembler can calculate this offset at compile time. It can say, I know the offset of hex template from the start of my boot sector code, which is this, and I know number 2. These are both constants, so it can just calculate this. So this is actually just a straightforward address, and this will translate to a straightforward address when it gets compiled, and it will be an offset based on this org value. So it would be the actual memory address of hex template plus 2 would be 7C00, which is where BIOS load is in memory, plus hex template, so plus the offset from this from the start of our boot sector code, and then plus 2. But either way, this is just a constant value. But in this case, you'll see that I've got bx plus hexabet here, and the compiler, the assembler, when it compiles it, it doesn't know what value is stored in bx. So this is something different actually. This is actually just a more complex way that the CPU can do addressing, and you see this used in compiled code, often for accessing arguments from the stack without popping them off the stack. We'll look at that later, but this is quite handy for doing this kind of stuff. It's just saying take the address that's in bx, because remember I'm using square brackets here, so it's loading what's stored in that address in memory into bx. But here it's just modifying it slightly, it's just adding an offset to what's stored in bx. So it's very useful. Okay, let's. You can mull over these things and think about them. I'm just showing you. If you've done this before, it might make more sense, but I'm just giving you things to play around with, really. Okay, so now we've printed the first character. That's good, but now we want to print the other digits too. So we want to print 2, 3, 4. So I'm just going to copy this block of code and do the next value. So what we want to do is, now what we want to do is print this number 2. So we want to shift it down again, because what we want to change this into is just the byte 2, okay, the value 2, rather than, we want to isolate this 4 bits. So to do that, I've copied the code, and rather than shifting it 12 bits, there's only 8 bits to shift it down. Okay, so we're shifting this 4 bits and then another 4 bits, and it's 8 bits. So what we're doing now is we want to convert this thing to OX naught, and it was a 2 we wanted, so we want to convert it to that. So we're going to shift it by 8 bits to the right, and then we're going to print it out in the same way. But we're not going to print it at hex template the second. We're not going to print it at the second offset from the start of the template. We're going to print it at the next one, this question mark here. Otherwise we'll write it over the top of the first digit, so we'll just include this. Let's see what happens. Something's gone wrong there, because it's not printed the rest of the string. Something, yeah, it's gone wrong. Let's have a look. So what I wanted was to isolate this value by shifting it right, but I mentioned earlier masking, and that's what we need to do here. The problem is when we shift this right now, it's actually going to have this value like that, which is not what we wanted, because it's just shifted this value 8 bits to the right, which is giving us this value here. The higher bits will just be set to 0 when we shift right. But what we want to do actually is mask it. So we want to do we want to AND it with bx with OX. In fact, the nicest way to do this is if we shift it first. So we've shifted it now, so we've got this, but actually we just want it to be 2. So now we can do AND bx OX not F. Now what this means, I might as well just write my comment here, it makes it clearer. So this means take bx to be that value. We've isolated the second 2 bits now. So that AND is just, I've just used an AND, and an AND, well, if you remember you probably looked at the logic like AND gates. So if you have a 1 and a 1, and you AND them, it goes on 1. If you anything else will give you a 0. Okay. So if I put F in here for the lower digit, that's F would translate to for 1 bit set. Okay. So if I AND this with any number, it will keep only those lower 4 bits in the value. So in this case it will isolate the lower 4 bits, which will be the lowest hexadecimal digit. So there we go. So we've shifted 1, 2, 3, 4. We've shifted it 2 bits to the right, so we got 1, 2, because we wanted to move the 2 into this position so that we can convert it to a byte 2, that 4 digits, and then we ANDed it with this mask to get this. So let's have a look if this works. There we go, we've got 1, 2, so well, now it's just a case of following what we've done before to do the other characters. So if we copy this, okay, so now what we want to do is we want to isolate this digit here. So we're going to shift it right by 4 bits. We're going to mask it to the lower bits so that we let me just rewrite this, because now if we shift that 4 bits, we're now going to have 1, 2, 3. And now if we AND it with this mask, we're going to isolate the lower 4 bits, so we should get a 3 in there. And just I'll make a mistake on purpose just to show you that we need to update something else. Now I've got this 1, 0. Well, this is wrong. I wanted to print that. I wanted to replace that question mark, and I did it slightly wrong. I also put 84 in there, which is not good. So I've shifted it 4 bits to the right. I've masked the lower 4 bits off, so we keep those and get rid of all the other ones. So the 1 and the 2 there. And now I want to replace hex template plus 4, which is going to be, that's 0, 1, 2, 3, 4. It's going to be the third digit. Let's check that works. 0x123, yeah, this is good. I hope again when you're looking at this you're thinking it's so easy to do this in like Python or some high level language, but when you come to doing this stuff, when you've got no libraries or anything that you can use, no other existing functions that somebody else has written for you, then you can appreciate that it's even difficult to print to print a hexadecimal value from memory. But that's why it's good to try these things, because then you come to appreciate them. Let me do this. And you've got to remember that this is going to be a very, very useful function at this stage, because one thing is that when we're working at this low level in a boot sector, we need all the help we can get. But there's no debugger or anything that we can say, trace through our assembly instructions and see how the values are being set. So if we can have a function that allows us to print a hexadecimal value that's just any value that we've plucked from memory, then it gives us an insight into how we're modifying the computer, and we can verify whether we're doing it in the correct way. And like I said before, we're going to load some more data from the disk, and we need to verify that we've properly loaded it, because there's lots of things that can go wrong and lots of mistakes we can make. So without this feedback, we're kind of blind, really. It's very, very useful. So now I'm going to do the last digit. So, well, 1, 2, 3, 4. I don't need to shift that one because the last digit is already at the lowest place there. And then I just mask it off, which should give me a 4. And I want to replace this as the last digit in my string here, which is offset 5. 0, 1, 2, 3, 4, 5. Yeah. So let's just run that. Hey, there we go. We can print the hexadecimal string now. Now, we're printing a string that we're printing a value that we put in there, but the real benefit of this is that we can now grab values from memory and print those. Before I do that, let me just recap on this function that I created. First of all, we've got a lot of repetition of code here, which is never a good idea. But what I said is that it's more important at this stage to learn how to do this than to optimize things. So I'm going to leave this as it is, and you can play around with optimizing it. You could do this in a loop, by every time you go around the loop, each iteration of the loop could represent a digit that you're translating from the value into the ASCII character. Here we go. Let me just check. Let me just put a different number in here. See what that does. Put A, B, C, D. There we go. So we're printing those. That's very good. Now, let's just confirm something that we assumed before. So I said that we get loaded to this address in memory. We've sort of already confirmed that because we played around with this before. But what I'm going to do is see if I can use my printx function to print out the magic number at the end of my boot sector. Now, if you remember, we had to put this magic number at the end of our boot sector, this value AA55, in order for BIOS to say that we're a bootable sector to load us and then execute us. Otherwise, it just ignores it as just a normal data sector on a disk. So this marked it's bootable. But what isn't, I guess what we can't assume is that BIOS might have loaded that sector, but it may not have actually loaded the magic number into memory. Maybe once it had decided that we're bootable, there's no need to copy that byte into memory, those 2 bytes at the end. So let's see if we can print it out, see if it's there or not. That can be our first use of our function. So, what we should be able to do then is move any address into dx to print out its value. Now, I'll keep going over this stuff, sorry if it's familiar to you already, but I'm moving this. This means move or copy this value, this constant value into dx. But if I do this, oh wait, let's put 1, 2, 3, 4. This means move the value that's stored at this address in memory into dx and print that. So let's see what this does for a start. Okay, it's printed 0, so that means that particular address in memory, 0x1234, has got 0 in it. Okay. Well, how can we find our magic number? Well, we know that BIOS loaded us at 7C00, so we can start with this. 7C00. So let's just see what gets loaded there. On here it says 00BD. Now, if I look in, it's always good to do to play around, to look at the stuff that your assembler is creating. So if I look at if I use a hex editor to look at my binary that was created, and I look in here, then what I should see is, yeah, so 00BD is the first word. Remember that the bytes in memory are actually stored in reverse order, so that the least significant byte comes before the most significant byte on this interrupt. So this is what I saw. This is when I printed the first address of, so the first 16 bits of my boot sector. This is what I saw, which is what the assembler compiled. So this instruction will be whatever that means to the CPU. We don't need to care. But anyway, I printed a value that was loaded into memory. But let's see if we can print the magic number. So to do that, we know that our boot sector is 512 bytes long. So first of all, let's just try adding 512 to this. A bit naively, as we'll see. But okay, that's a 00. What we wanted to print actually was not. We didn't want to add 512 to it because it's the last 2 bytes that are the magic number, not the magic number doesn't come after our sector. So actually, we would want to print this. So this should have the magic number. There it is. So what I've just shown is that BIOS did load the magic number that was on the end of our boot sector into memory, which makes sense really, because why should it bother worry about stripping something like that out? It's just easy to copy the whole sector into memory. So it is there. What was also interesting though when I did 512 is that that there's nothing in the value after our boot sector, which we might infer if we look at our remember this diagram that I had. If our boot sector is here and the top of our boot sector is here, then this was marked as free space, and because there's no byte set in there, I can assume that it's not being used yet. Not to assume that, I mean, there's no reason to assume that all memory is 0 to start with anyway. It probably is, but I don't know. But anyway, I showed that the magic number is at the end of memory at this address, and I showed that beyond that it was 0. So this is good. So we're going to have a look now at doing something else, which is going to be just a bit of a detour really. Let me just, that's okay as it is. What we're going to do now is just have a little bit of a play around with memory. So we found the magic number, that's good. Let me just explain this function, this printx function, okay? Before we move on, just in case you missed part of it. So our goal with the printx function was to store a 16-bit value in the DX register, call our printx function, and that would print it. It would print it to the screen as ASCII characters. So the ASCII characters are something that we can understand, but something that the computer doesn't really care about. The computer just sees 16 bits in memory, ones and zeros, 16 of them. We want to convert that to hexadecimal, which is our own way of understanding, of representing that binary data. The computer doesn't care about it. So I need to convert that into hexadecimal. And hexadecimal is a convenient way of representing binary data because we can easily translate between 4-bit chunks of that. So each digit of the hexadecimal number is 4 bits, and we can easily translate that to and from a binary representation. So what the function does, it basically isolates each of these digits by shifting and masking them. So it will shift this, for example, if we're printing this one and we wanted to represent this 8, we would shift it all the way down to the end and mask it off so that it's only the 8 value if there was some other digits before it. And then it converts that 8, that 4-bit value, into an ASCII character that represents it. So that will be 0, 1, 2, 3, A, B, C, D, F. And I use my hexabet to do that conversion. Otherwise, you have to do a bit more, have a bit more branching and logic in there. So let's have a play around with something else now. Now what I want to do, because we've got this function now that can print hexadecimal values in memory to the screen. So what I want to do now is just have a poke around in BIOS and memory, see if we can find a string in BIOS and then use that to find other strings to see what's in memory really. I showed you this diagram before and I said that, you know, memory isn't just empty when your boot sector starts. BIOS has already loaded itself and it's got code in there and data. So let's just try and verify that a bit. Let's have a poke around and see if we can find something interesting. Now what I want to do now is, well, I've called it fishing in BIOS. So we're going to look for some common strings in BIOS. And then that's going to show us, it's going to demonstrate how we can loop through memory, and it's also later on we're going to look at how we can use segments as well to reach further into higher memory. And we're going to see if we can find some strings. So let's have a look. And if we find some interesting strings, then it's quite a nice result. Okay, so let's get my code back. We're going to create another function now, and I'll just comment this one out for now. So the first thing I want to do is see if I can find a string in BIOS. Now the approach I'm taking here is that I am assuming that somewhere in that memory where BIOS is loaded there's a string, an ASCII string that says BIOS. When you boot your computer you get the BIOS configuration screen if you press like F2 or escape or something, and you'll see that it talks about BIOS and stuff like that. And I think every time I've loaded BIOS it said something about BIOS. So I'm going to search for a string BIOS to see if we can find where that is stored in memory. And that, if we find a string BIOS that matches BIOS, then there might be other strings around that have more information about BIOS. So we're just going to search memory. Now, because we're not in a high-level language, this is going to be more complicated than we would expect at first. But we'll build it up again like with the printx. So we're going to search through memory until we find something interesting in the string BIOS, and then we're going to hang there and print out the address that we found it at. And then later on we can just use our printhex function to print out things around that address to see what else is there. So this builds on all the stuff that we've learned so far. So let's call the function find BIOS string. So this is a label. Let's just move this down. We're going to not worry too much about that for now. In fact, we can move this printx into our oh, we'll leave it there, it doesn't matter, we'll leave it there. But we're going to ignore it now. We're going to focus on this find BIOS string function. So what do we want to do? We're going to call this function find BIOS string, and then we're going to hang. And this find BIOS string is just going to search through memory until it finds the characters BIOS, and then it's going to hang there and tell us what address it found it at. So I'm running my code now and it doesn't do anything yet because I'm just building it up. So what do we want to do? We want to search through memory, so we're going to have some kind of loop. So let's just use the label, let's call it loop. Let's call it search loop. Okay, so in my search loop, let me use a register for a counter, and it's going to start at byte 0, we're going to increment it, and then we're going to look at byte 1, 2, 3. We're going to search through memory like that, starting at 0. So our thing is going to start here, and it's going to just search all the way up, looking for an interesting string. So we've got our search loop, and first of all let's just start it off. let's just put jump search loop. This is going to give us an endless jump. Don't try and overcomplicate things to start with. I'm going to use a register for the counter, and I don't know, let's use bx. So if I do move bx 0, and that's going to represent the first address we're going to look at. And all I'm going to do is print out, I'm going to print out the address that I'm looking at. So move bx, bx, which is the current address I'm looking at, and then I'm going to call my printhex function to print that out, and then I'm going to print the contents of that address to the screen as well. So I'm going to be printing two things each time I go around the loop. I'm going to print the address I'm looking at and the contents of that thing. So let's do move dx. Remember, dx is the argument to printx that stores the value we want to print. So I'm going to do this. Okay, and then I'm going to call printhex. I'm going to make a few mistakes on purpose here, just because these are things that you'll probably make when you start doing this stuff, as you always do when you're programming. There we go, we've got lots of stuff printed. Wow, look at that. Lots and lots of stuff. First of all, I've forgotten to increment bx in my loop, so I'm just printing the same address every time. So I'm just going to use the inc CPU function for the bx register, so it just adds one to it. And what I should see now is it should be printing different things, so it's printing lots of them. So let's have a look. So each time around the loop, so increment bx. Okay, let's just print the address for now and just check that our that bx is working properly. Ooh, see, there's a lot of stuff there, so it's hard to see. But that's that should be looping through the addresses. One thing I can do is just if I just duplicate this code, to do it twice, and then do a hang, so that I just hang the CPU at that point, and let's just see if that does. So it's printing 00 and 3131. So first of all, what we expected there was that it would be printing, it would just be printing, bx would just be going 0, 1, 2, 3, 4. But let me just check my printhex function. And I've made the mistake that I said that we shouldn't make when we define functions before. Remember that there's no such thing as a function, and if a function changes some registers, then when the function returns, those registers will still be changed. So if you do change registers in a function, you should usually, so that the caller doesn't expect any strange side effects, you'll want to preserve the original value of that register that you're going to change. So we're going to push it on the stack and then pop it on the stack at the end. That's all we're going to do. So here I'm going to do push bx, because we're changing bx. Let's push si as well, because we're changing si. And then just before we return, we pop them off in the order that we put them on, the reverse order. So we're going to pop off si, and we're going to pop off bx. So this means when we return, it should return with the original values in there. So that's why when I was doing this, I said you should really just, every time you write a bit of code, just check that it's working as you expect. Otherwise you end up looking for these things for ages. Now let's just check that, so bx now is incrementing as I expect. So there's no strange, it's not being modified inside that printhex function now, because it gets preserved on the stack. Good. So now when I run this loop, I should see my values increasing. It's doing it very quickly, which is good. But this is just looping through memory now. So these are memory addresses. being incremented. So now what I want to do is, okay, I'm going to print out the value stored at those. But when I'm printing so much information, it's not too useful because I can't read it fast enough. So now what I'm going to do is I'm looping through memory, and rather than printing out the thing that's stored at memory, or even printing out memory, what I'm going to do is I want to see, I'm going to be looking for the string bias. So I'm going to grab the value from that address in memory that I'm searching, grab a character and compare it and see if it's the letter B. Okay, and then my strategy is that if it's B, for now I'm going to hang, but then what I'm going to do is I'm going to say if the first one's B and then the next address in memory is I, and then the next address in memory is O, and then the next address in memory is S, so it's the BIOS string. If I've matched that string, those 4 characters, then I'm going to hang and print the address out. So this is our search string function, written in assembly, very low level. So let's do that. So I'm going to, I want to print out well, first of all I want to do a comparison with what's in bx. So I want to say compare, now if I'm, probably the easiest way to do this is to, I want to move the character that's stored at that address into somewhere. Now I'm going to do it, let me store it in the AL register for example. So if I do move AL bx, this is saying move the character. I'm using AL because I'm just interested in a single byte, an 8-bit value. AX is 16 bits wide, AL is the lower 4 bits. So I'm loading the character that's stored at bx into AL, and now what I'm going to do is just do a comparison of AL to see if it equals character B. If it doesn't, then I want to continue my loop. Okay. So let me have a label here called continue. Okay. There's lots of different ways we can do this and structure it, but in fact let me just, first of all I'm going to do that comparison, and all I'm going to do is say, I don't know, if it's not a B, okay, if it's not the B character, then I just want to continue my search. So like I was doing, let's just have a continue. Let's call it continue search, and let's put that down there. And that can, all that does is it gives us a place to jump to. Come back. Gives us a place to jump to that will then go here, and then it will go back around to the loop. So it will increment bx and it will carry on looking around the loop. If we don't jump to that, then let's just hang. So if we found a B, let's just hang. First of all, we need to do our comparison function. So I'm going to say, I don't know, if it's not equal to a B, then I'm going to jump to continue around the loop. So I'm going to use the JNE, jump not equal. So JNE. So if AL doesn't hold a B, so the value in memory is not a B, I'm going to jump to continue search. If it does have a B, I'm going to hang here. So, and before I hang, I'm going to print out the address. So I'm going to move the address in bx. I'm going to move bx into dx, and then call printx to print the address that I found a B at. Okay, let's run this and see what happens. See if I've made any mistakes. Okay, so it's printed an address, so I think it's found a B at that address, which is good. Now, what I will do as well, while we're doing this, just to make it, give us an initial goal to go at, I'm going to have a label here called find me. I'm going to have db, I'm going to, inside my own boot sector, I'm going to put the string bios to see if we can find that with our function. Okay, so find me. So we've got something to look for initially. Now, so now what I've got is I'm checking for, so each time I go around the loop, I take the address that's in bx, so it starts with 0. I move the byte that's stored in bx, so the byte stored at that address in memory. So initially it's going to be the first byte in memory at address 0. Store that in AL and compare that to a B. Okay, so if that first byte in memory was a B, then I would continue past this jump not equal down to here and print out the address that I found that B at. If it's not a B, then I jump to continue search, which jumps over my hanging code, and it just goes to the end of the loop block, and it increments bx and it jumps back to the start of the loop and it starts searching from the next address. So I can find a B. Now I just need to extend this now to look for the word BIOS. Okay, so I'm looking at bx and I'm saying, does it contain a B? If it doesn't, jump to continue to search. And now I'm going to copy that code. Like I said, we can optimize this and we can make it look for arbitrary strings, but it's not useful at this early stage. Now what I'm going to do is, so assuming that we get to this code now, this instruction, it means that we didn't jump to continue the search, which means that we found a B already. So now I'm going to say, look in the next address, the next byte in memory, and see if that's an I. And if it's not, continue. So now we should be able to find the string BI in memory. Oh, now I've got an address there, 7C08. And looking at that 7C, I know that BIOS loaded me to 7C00, so there's a good chance that this is the start. This has now matched the start of our string BIOS that I just added to my boot sector. Now let me just close that down and just add the rest of the things, the characters. So now we want to see if the next character after we found an I is an O, because we're looking for the string BIOS. And let me add the other one too, right, as well. So now I'm saying if I find the string BIOS and I get all the way down to here and it's matched all those characters in that sequence, then I'm going to run this code which prints out the address that it found it at. Otherwise I'm going to continue looking. So let's do this again. Okay, so we found the string BIOS address in memory 7C0A, which falls within our boot sector. And if I look at my, so remember this OA, because this is an offset from the start of our boot sector code. Remember OA. So let me just check that. So find me, I had this string BIOS, and if I look in the hex code generated for my boot sector, or my hex editor, I should find that this label, after it's padded down by all these instructions, lands at OA. Which is 10, so it's 10 decimal, so it's the 10th byte from the start of my boot sector. That's what I searched for and found in memory. So let me just check in my hex editor the 10th byte, which was OA. So I'm looking down here at this offset. So when I go to OA, alright, there it is, 4249. These are the ASCII characters for the characters BIOS. So that's it. So my search function is working. It's found the string BIOS in my own code. Now I wasn't really that interested in doing that. I wanted to see if the BIOS string was somewhere else in memory. So all I've done so far is found that I've got the string BIOS in my boot sector, which I put there. I want to search up here and see if I can find the string up there. So in code that was loaded before my boot sector loaded, which was the BIOS code. So I'm going to get rid of this this now, because I don't want any false positives. Now if I run my function again, see if it finds it. It's not found it. Okay. So does that mean that BIOS, the string BIOS, doesn't exist in memory? No, it doesn't actually, because now there's something we need to do with segments. I mentioned segments before. By using bx to search through memory, bx, the register in 16-bit mode when your computer boots, it can only represent, well, the maximum address that I can store in bx is 0x FFFFF. which gives me about 64 kilobytes of memory that I can read, which, if I'm searching through memory, will take me somewhere up here, just above here, so I'm not even going to reach up to here. Remember, that was a limitation of 16-bit addressing. Now the CPU allows us to reach further into memory by using segments, which I had a little look at last time, but now I'm going to just demonstrate that. So we want to reach up higher in memory. Now the way the segments work is there are these segment registers, often ending in S, like DS, CS, and there are general purpose ones like ES, which I'm going to use. And if I store a value in those, a 16-bit value, then what that means is when the CPU addresses memory with a 16-bit address, it doesn't just address that 16-bit address value, it takes what was stored in the segment register, shifts it 4 bits to the left, and then adds that to the address that I'm accessing. So basically what that means is it gives us another 4 bits of memory we can address, which allows us to search through to reach up to about a megabyte of memory, I think, if I'm right. So we're going to have to use that if we want to search for it. So let me just adapt this now. So we don't just want to increment bx, but we want to make sure that when bx gets to, let me just put some comments in here. So currently what's happening is when I call increment bx, if the current value of bx was ffffff, and then I do an increment, it will wrap back round to 000. So essentially the reason the thing didn't print anything was because it just kept searching the initial 64k of memory for that byte string. But now I want to search further, so I need to do a bit of a condition here and say whenever, the easiest way to do this is if I've incremented bx, and after incrementing it now holds 000. If it's wrapped around again, then I want to change the segment register to increment that, so that what I actually access would be OX. The segment register effectively gives us another 4 bits on top of our value. So what we want to do is after we add a value and it overflows our 16 bits, we want to then have it so that in our segment register we have this 4 bits added to our address, so that we then start searching through this, so then we'll do 1, 2, 3 until we got to FFFFF, and then we wrap round to 2, and then we go. So this is how we want to search. So let me have a look at how to do that then. So we need a condition. Well, first of all we need to set our segment register. Now I'm going to use the general purpose segment register. So the segment registers for there's one for the code segment, there's one for data segment, and there's one for the stack segment, which just mean that whenever you reference a stack with a 16-bit address, the actual address that the CPU uses when it accesses memory is it's the whatever we store in the stack segment register is shifted 4 bits to the right and added to the address that we're referencing for the stack. And the same for code and data. So code, when we're executing instructions, the next instruction that executes is not just the 16-bit value stored in the instruction pointer, but it's that with the CS segment value shifted left by 4 bits and then added to it. It's like let me just write some code in here. The best way is to play around with stuff to see if it works. But what I'm going to do is I'm going to use the ES register. Now, first of all, I'll make some mistakes on purpose. I want to initially start the segment with a value 0, so that so the value in bx when I'm searching is the initial addresses in memory starting at 0. Okay, so I don't want any segmentation being added to that value. I want to start with a segment value of 0. So I move that into there. Now if I just try and run this, I'll get an error. It's saying that I can't combine this opcode and operands, and all that means is that if I go back to here, is that I can't move a constant value directly into ES. I have to move it from another register, and in this case the most convenient thing to do is to move BX into ES, which just means I set BX to 0, and then I copy the value in BX, which was 0, into ES. So now both ES and BX are 0. Let me put some comments. So ES goes to 0, and BX goes to 0. Okay. Don't know why I did that in capital letters. It's just, it doesn't really matter. I'll leave it. It's because I put caps lock on. Anyway, so now we've got this thing. So initially, when I run this code, it's going to do exactly the same thing as it did before, because I'm not incrementing the segment register value. What I want to do now is I want to compare. I said that when I increment BX, if I start at 0 and increment it, it's going to go to 1. And if that ever wraps back around to 0, it means that then I want to increase my segment register to search for the next few bytes in memory. So what I'm going to do then is I'm going to have a condition here. I'm going to say compare BX to 0. So if it's wrapped around BX, if it has wrapped around, let me think, what's the easiest way to do this? Well, if I've got my continue search, well, let's just put the code in first, and then we'll figure out how to make sure that our branches are isolated. So I'm comparing BX to 0. If it is 0, so if I do a jump equal, and then I do, let me call it increment segment. So we'll jump to there. Trying to think of the easiest way to do this, because I need to jump back here again. So we can jump back to search loop. This is fine. Okay, you can change your the order of how you do these things infinitely, but I'm going to do it like this for now. So I'm going to jump to this label increment segment, which is I'm going to put down here. I need to make sure that I okay, so if I take this, so I'm going to compare it to 0, and I'm going to say just down here somewhere, let me have a label called increment segment. Okay, and when this is finished, this is going to jump back to the start of the search loop. Okay, after it's incremented the segment. So here I'm doing a comparison. So if it's 0, if it's wrapped, we're going to say if it is 0, so jump if equal to increment segment, and that will increment the segment and then jump back. So let's just run our code. So it does nothing at the moment, so we need to increment that segment first of all. Okay, so let me just do this, and then it's a good way of explaining how it works is to demonstrate it, how the segments work. But I'm going to take my segment, and I'm going to do this. I'm going to add to my segment. So add to. I'm going to make a mistake here as well. So my segment is in ES. That's my segment register. I'm going to add to this 1000. I'll explain this. Invalid opcodes. Yep. I said I'd make a mistake. Again, we can't just do an add on the segment register. We have to copy the value out of it into a general purpose register, another register, add to it, and then copy it back again. These are CPU limitations to do with the hardware. In this case, it's probably more of how the CPU is being emulated in 16-bit mode. Like the computer could probably do it, but we boot the computer in 16-bit mode, and it follows the same architecture as it did for the initial x86 machines. Anyway, we need to do this first. So first of all, we need to move the value, move into CX, the value of ES, the current value, and then we want, sorry, that should be CX, and then we're going to add this to CX, and then we're going to move it back again. So we're basically just incrementing ES by that value, and I'll explain why I use that value in a minute. Let's just see what happens now. Looks okay. So we start searching. It's not found anything yet. It should be able to search through a megabyte of memory quicker than that, even in an emulator. So something's not right. And what's happening is that so I'm using this ES general purpose segment register, and actually when I reference memory like this, so when I say move the address BX into AL, what that translates to is actually, by default, it's using the data segment register to calculate the actual address of what's in BX. So what this is actually representing is it's going to be whatever stored in the data segment register shifted to the left by 4 bits and then added to what's in BX is the address that's going to be stored. And because I'm not changing the data segment register, I'm still not searching outside of the first 64 kilobits of memory. I'm not actually using my segments yet. So what I can do here when I'm addressing is that I can put the segment that I want to use on here, and I'll do it for all of these. Okay, so now what this is saying is that use the address in BX, which I'm incrementing, so the 16-bit address in BX, but use the segment, apply the segment register to that value to get a 5-bit address. How many bits have I got? So 20-bit address, because the segment adds another 4 bits onto the top of my address, and it's using the ES register, which is the one that I'm cycling through. So now if I run this, where'd it go? It's found an address. Okay. So it's saying there that at address 8383 is found that string BIOS. Okay. If I also what I want to do is not just print the BX register, the address in there, because I'm changing the segment registers too. So I'm going to print out, before I print the address that I found it at, I'm also going to print out the current value of this segment register ES. Okay, so what it's saying is that when I set the segment register to C000, and when I'm searching through memory, when I reach up to C000 as a segment, and then it finds that the 16-bit address added to this shifted to the left by 4 bits, because that's how segments work. I said when I first talked about it that it wasn't intuitive, but it's just a way of gaining an extra 4 bits on an address. So what this address actually translates to is, just open the terminal, is OX C 8383. That's what that translates to, because whatever's in the segment address that I'm using, it gets shifted. So this C000 will get shifted 4 bits to the right. I'm just writing it in C notation or something, and then that will give us this value C000, and then it gets added to OX83, whatever was in the BX register, the 16-bit address, which gives me the physical address OXC 8383. There we go. So let's just close close this. So we found that 8383 C000 that we found the string BIOS in memory, and that wasn't in our code. And if we look in this diagram, we see that it's actually up here, so C000, it was somewhere up here that it's found that BIOS string, which is in what's labelled as BIOS in this memory map, common memory map for a DX86 machine. So we found a BIOS string in there, which seems to tally with what we already know. Now I could go and print that string with that address. So rather than, if I just do a jump here, if I jump infinitely so I don't do anything. So now I've found that string, I should be able to call my print string printhex with what's stored at that memory address. So remember, printhex uses dx as its argument, so I'm moving to dx, and what's stored at ox 8383, and I print it. Well, first of all, I'm making a mistake on purpose again. There we go. It's that. It's not BIOS. Actually, sorry, I didn't want printhex. I wanted to print the string because we found a string in memory. So what I wanted to do actually was move the address into this. So let's see what this does. Okay, that's not printing anything. Because I've not put my, I need to set the segment register. Now I'm going to show you that when I call print string, it's going to look at this address, 16-bit address 8383, but it will also add the data segment offset to that address to figure out, well, to map to the actual address in memory. So if I want this to print OXC8383, which is where that string was found, then I've got to store in my DS register OXC00. Oh, invalid opcode. I made that mistake before. Remember, I have to, if I want to store a value in one of these segment registers, I have to move it to another register first. So let's put it in AX, and then if I do DS, so the data segment AX, now let's do this. Here we go. Look. So we found a string in BIOS. We found the address of it using our search function. We had to use we had to manipulate the segment register so that we could reach higher into memory, to reach higher than just the first 64 kilobytes, which we could address with 16 bit addresses. And we've found the address of the string BIOS, because that's what we matched in our search string. And now that I've printed that address that we found, I see that there's actually more to that string, so it says BIOS serious extension. So that's some string that was in the BIOS area in memory. Now if I just look around here, I've got some addresses that I found. So for example, if I put 833, I think this is right. Yeah, so it's just, if I put an address slightly earlier, 8330. There we go. So we found that there's a string there. So it's just saying Cirrus compatible VGA is detected. So so though it seems that there's a few strings stored in memory there, and those things will probably relate to BIOS error messages, or even to the BIOS configuration application that loads when you like press escape or whatever, F2. So I found a string in memory now, which is good. Now later on I'll just run that in VirtualBox as well to show you that the BIOS in QEMU, this emulator I'm using, is different to the BIOS that's used in VirtualBox. But remember that I said that the way we interface with BIOS is through interrupts, so it doesn't matter if the memory layout is different in BIOS, as long as there's a common way of reaching functions in it, so using interrupts, for example. So, right, let me just recap on that, and then you can think about it. I wanted to find a string in memory. I wanted to see if there was any interesting strings that we could look at in BIOS
in the BIOS areas of memory. So I wrote a search function, and the way the search function works is it just goes around in a search loop, and each time around the loop it increments the BX register by 1, and then every time round the loop it looks at the byte that's stored in the address of the BX register, and it checks if that's a B. If it's not a B, then it just jumps to continue the search down to here, and then that just increments the byte, and it will go back and loop to the top, and then it will look for another match in a B. And if it doesn't find a match for that B, then it just keeps looping round. If after it's found a B, it then finds an I, then it doesn't jump around again. It checks for another one. It says, so the next character after the I is at an O, and the next character after the O is at an S. And if we find this string BIOS, then it never jumps back to continue the search. It comes down here, and it just takes, well, first of all, it takes that 16-bit address that we had in BX, and it prints it out. Okay, but the initial problem we had was that without using segmenting, without manipulating the segment registers, we would only ever be searching in the first 16 addresses would only ever be 16 bits wide, and we'd only be searching in the first 64 kilobytes of memory. So we didn't find the BIOS string when we did that. So then what we did was we manipulated the ES register, which is just a general purpose segment register that we can use for accessing more of memory. So we started that at 0, and every time our 16-bit address overflowed, we just incremented the, well, we didn't increment it, we added this value, hexadecimal 1000, to it, which means that when this segment gets applied to what's in BX, like when we use the addressing like this, so we say get the byte that's stored in BX, but using the ES segment to modify that address up to 20 bits, and it's that. So we're using the segment there to look further into memory, and we're incrementing the segment each time so that we wrap around. So what this actually means when it says OX 1000, that actually translates to, because it gets shifted when it gets added to the address in like BX, it gets shifted by 4 bits, so it becomes 1000, and then it's this value that gets added to our value in BX. So when we add it to BX, it becomes well, if BX was like 1, 2, 3, 4 or something, then this would become OX 1, 1, 2, 3, 4. So we can reach further up into memory because we can set this high 4 bits of the address. And once we had that segmenting, and we used it explicitly here, we said to use the segment register ES when we're accessing memory, we could search further up, and then we found a BIOS string up in memory, and once we found the BIOS string, then we used that thing that we found to look for other strings in the area just to print them out. So we first of all we used the 16-bit address that we found, but we had to set the segment to the same segment that it was found in, and in this case I used the data segment because that's what gets applied to any data access by default. Okay, so I set this in the data segment. If I didn't do that, then this would just represent 8330 in memory, whereas if I set, for example, DS to I don't know, if I set DS to, well, which is what I did, so I set it to C000, then what this value here actually translates to in physical memory is OXC 8330, like that. So we reach up into here, and that's where we found the string, and then we printed it out. Just lastly, before I finish on this one, first of all, it's good to play around with this stuff to confirm, you know, like what you've learnt. But this bit is not really essential for what we're doing next. We printed a hexadecimal string, and that's going to allow us to, when we load more data from the disk later on that's going to allow us to see what's in there to verify that it's worked. But this is just really an exercise in building on writing functions and using logic. Let me just, if I run this, so there's my string that I found there. If I'm going to run this in VirtualBox and see what we find at that address in VirtualBox. If I just get my, say, to run these commands to build an image that's suitable for VirtualBox. Okay, now I just made an ISO. So in my virtual machine, I'm going to load that virtual disk file, this one, in my machine, as though it was a CD. I'm going to power on the machine and see what happens. It's printed. There we go. So when I ran VirtualBox, it printed a different message, and we see that there's this string in the VirtualBox BIOS. So VirtualBox has its own BIOS code, which makes sense because VirtualBox is it kind of emulates or virtualizes the way BIOS works, but in a virtual machine. So when you print to the screen in VirtualBox, it doesn't print to a screen; it prints to a virtual screen. Anyway, there we go. So we found some strings, and we confirmed that that BIOS was in a place that we expected BIOS to be, somewhere around here. We'll probably find other things in here, other strings. Like you might want to try searching for strings like copyright, and you might find copyright strings that are close to certain bits of code that are already loaded into memory. So there we go. Thank you very much, and just have a play around with those things, and you could, with a bit more time, you could improve on those algorithms if you wanted to optimize them, condensing them. Just have a play around really, see how it all works. And in the next lecture, we're going to look at loading stuff from a disk, and then which is going to allow us to later